Hello everyone, my name is Nidhi Singh. I'm an assistant professor in the Columbia School of Suresh Gyan Vihar University, Jaipur. Today we are going to discuss the Aliphatic amines. So in the last lecture, we have already discussed the stereochemistry and the stereochemistry of amine, the electricity of amines and the properties of amines, as well as the nomenclature of amines and what are aliphatic amines. So here today we are going to discuss the so the learning objective is that here we are going to know what learn about amines, and also we are going to study about preparative preparation of alkyl and aryl amines, and the student outcome is that they are going to know about what are amines and also learn about the preparative method of alkyl and the aryl amines. So here in this we are going to here in this today's topic, we are going to discuss about the preparative method of alkyl and amines and how they are prepared, or how they are prepared from the different reagents and from the different compounds. These alkyl and the aryl amines are prepared. So in this we are going to discuss. Today we are going to discuss about this thing. So here we are. So the aromatic amines are weaker bases than ammonia and aliphatic amines, and the less basic character of aniline can be explained on the following basis. So these aromatic amines are weaker bases than ammonia and aliphatic amines, and the less basic character of aniline can be explained on the following basis. So here the less basicity of this, the less basic of this. Character of this aniline, where it is explained that how the anilines, why the anilines are less basic than the ammonia and the aliphatic amines. So here the delocalization of the unshared electron pair on nitrogen atom. So first, through which we can explain the aromatic amines that are weaker bases than the ammonia and the aliphatic is the first point. Delocalization of the unshared electron pair on nitrogen atom, the resonance stabilization of the free base form of aromatic amines, and for aniline and other aryl amines, the resonance stabilization is the result of interaction of the unshared pair on nitrogen with the pi system of the aromatic ring. So due to its interaction, the electron pair on nitrogen is less available for reaction with acid. So no such resonance stabilization is possible for alkyl amine, and therefore the electron pair on the nitrogen of an alkyl amine is more available for reaction with acid. Alkyl amines are stronger bases than aryl amines. So here in the delocalization of unshared electron pair on nitrogen atom, the resonance stabilization. So then the stabilization of the free bases form of aromatic amines, and for aniline and other aryl amines. So the resonance stabilization here means that there is a resonance stabilization in the free bases. They are forming aromatic amines. So here in this, due to the resonance stabilization or the delocalization of the unshared pair of electrons on the nitrogen atom, they are acting as a free base. The aromatic amines are acting as a free base form, and for aniline, which is a aromatic amine, this is or the other aryl amines, or in case of other aryl amines, this resonance stabilization is a result of interaction of the unshared pair of nitrogen with the pi system of the aromatic ring. So here, this unshared pair of electrons that are present on the nitrogen atom, they are interacting with the pi system of the aromatic ring. As you all know that the benzene is having the pi system in this in their aromatic amines, so they are having the pi system in there because there are three pi electrons in the benzene ring, and they are delocalization. So their delocalization is involving with the nitrogen unshared pair of electron pair of the nitrogen atom. So So due to this interaction, the electron pair of nitrogen is less available for reaction with acid. So that is why the nitrogen, the electron pair that is present on the nitrogen, they are participating in the delocalization, participating with the delocalization of the pi system of the aromatic ring. So that is why the electric pairs present on the nitrogen are not interacting with the acid. So that is why their resistivity is low here. So no such resonance stabilization is possible for alkyl amine, and therefore the electron pair on the nitrogen is available for the reaction with acid. So in case of aliphatic amines, in case of aliphatic amines, they are not participating with the they are not participating in this resonance stabilization. Means they in the alkyl amines there is no resonance stabilization or the delocalization of the electron, and that is why the electron pairs that are present on the nitrogen atom that are not that are not participating in any delocalization. That is why they are readily available for the reaction with acids. That is why they are readily available for reaction with the acid, and the alkyl amines are stronger bases than aryl amines. So these alkyl amines, they are stronger bases than your aryl amines. So this is the delocalization means here that in case of your aromatic aryl amines, the nitrogen in as you compare the aliphatic amine with the aryl amines, the both of them the unshared pair of electron is present on the nitrogen atom. So in both the case, there is a unshared electron pair on nitrogen atom. But in case of this aryl amine, they are this electron pair is participating with the uh, 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 um, electrons that are present on the pi, or they are taking participation with the delocalization of the benzene ring that is happening in the benzene ring. So that is why this electron pair, this unshared electron pair, is not readily available for the reaction with the acid. So this is not available with the reaction with the acid. So that is why they are less basic than aliphatic amine. But in case of aliphatic amine, they are participating. Are they are not participating with any delocalization or any resonance stabilization. That is why their nitrogen unshared pair of electrons that are present on the nitrogen are readily available for the reaction with the acid. So here, that is why alkyl amines are stronger bases than aryl amines. So they are stronger bases than the alkyl amines, and this is the first point which is showing that the aromatic amines are weaker bases than the ammonia and the aliphatic amines. So in this reaction, you can see here that this is the structure of the aniline, and you can see that there is a delocalization. So there is a delocalization of the electron. So here, from here, the electron is moving to this point, from here this, and after that, this electron is also taking participation in this resonance. So here you can see this electron, from there they are forming a bond. So here the double bond is there, and after that this double bond is shifted to this position, and there is a negative charge on this. It is because on this carbon atom there is a pair of electron pair is present. So the interaction of the electron pair on nitrogen with the pi system of the aromatic ring. So here you can see this nitrogen, this electron pair that are present on this nitrogen atom, they are participating in this delocalization of the benzene ring. So after that, there is a formation of this three resonance stabilized structure, and no resonance possible with alkyl amine. If the nitrogen is attached to an alkyl group, then there is no resonance possible. That is why this electron pair, unshared pair of electrons, is readily available for the reaction. But in case of this, they are not readily available for the reaction. So, that is why it is showing that these aromatic amines are weaker bases than the alkyl amines as well as your ammonia. Next is your substituent effect. So in the substituent effect, the second factor contributing to the decreased basicity of the aromatic amines is the nitrogen withdrawing effect of the sp2 hybridized carbons of the aromatic ring compared with the sp3 hybridized carbon of aliphatic amine. So the substituent effect is the second factor that is contributing to the decreased basicity basicity of the aromatic amine is due to the electron withdrawing effect of the sp2 hybridized carbon of the aromatic ring compared to the sp3 hybridized carbon of aliphatic amine. So the second factor that is contributing, because that is showing the basicity, that is showing that the aromatic amines are having the less basic, they're having the less basicity than the aliphatic amines and the ammonia, that is a substituent effect. So in this case, it is due to the electron withdrawing effect of the sp2 hybridized carbon. So in the aromatic ring, the carbons which are forming a bond, and they are all sp2 hybridized. So they are electron withdrawing nature. So they are having the electron withdrawing nature as compared to the aliphatic. In the aliphatic, the carbons that are sp3 hybridized and they are having the nature is electron releasing. So that is why they are increasing the basicity of the aliphatic amines. But in case of aromatic ring, the electron this these carbons which are sp2 hybridized, they are showing the electron withdrawing effect. So they are showing the electron withdrawing effect. So these are the second factor contributing to the decreased basicity of aromatic amine is the electron withdrawing effect of the sp2 hybridized carbons of the aromatic amine compared with the sp3 hybridized carbons of the aliphatic amines. So the unshared pair of electrons on nitrogen. So the unshared pair of electron on the nitrogen. So the unshared pair of electrons. So the unshared pair of electron on nitrogen in an aromatic amine is pulled towards the ring, and therefore less available for protonation to form the conjugate acid of the amine. So the unshared, so the electrons that are present, the pair of electrons that are present on the nitrogen in the aromatic ring, these are pulled towards the ring. So they are the electrons are pulled towards the ring. So they are not readily available for the protonation or the reaction with the acid and to form a conjugate acid of the amine. So less available for the protonation to form the conjugate acid of the amine. So the electron with releasing group, that is your methyl, ethyl, and other alkyl groups, they are increasing the basicity of aromatic amines, whereas electron withdrawing groups, example halogen nitrocarbonyl group, they are decreasing the basicity of aromatic amines. So in this case, the substituent effect, the second factor that is involving in this basicity, decreased basicity of the aromatic ring is due to the sp2 hybridized carbon atom that are sp2 hybridized carbon that are present in the aromatic ring. And in case of the aliphatic amines, the sp3 hybridized carbons of the aliphatic amines are attached in the aliphatic amines, and that is why this sp2 hybridized carbon in the aromatic amine, they are showing the electron withdrawing group. So they are showing the electron withdrawing effect, and the unshared pair of electrons on nitrogen in an aromatic amine gives to the electrons that are present, unshared pair of electrons that are present on the nitrogen, they are pulled away from the nitrogen, and they are pulled towards the ring, and therefore these electrons are not readily available for the protonation, and therefore they to form the conjugate acid of the amine. So the electron releasing groups, for example, the methyl, ethyl, or the alkyl group or the other alkyl group, these are increasing the these increases the basicity, these are increasing the basicity of aromatic amines, this electron releasing groups, they are increasing the basicity of the aromatic amines, whereas the electron withdrawing groups, the electron withdrawing groups are decreasing the basicity of aromatic amines. So they are decreasing the basicity of the electron withdrawing group. Decrease, so the decrease in basicity, so the decrease in basicity on halogen substitution is due to the electron withdrawing inductive effect of the electronegative halogen. So here the basicity, so there is then decrease in basicity on halogen substitution, which is due to the electron withdrawing effect of the electronegative halogen. So here, if the halogen is substituted on this aromatic ring, then they are increasing the basicity of this nitrogen of this amine, because all the hydrogens are they are having the electron withdrawing effect, electron withdrawing inductive effect, which is due to the electronegativity halogen, because the halogens are electronegative and they have the electronegativity property on them, and that is why are always they are the withdrawing in groups. They are showing they are the withdrawing groups, and they are always showing the electron withdrawing inductive effect. So due to this property of this halogen, they are decreasing. They are decreasing the basicity of the halogens. They are decreasing the basicity of the aromatic amines, and the decrease in basicity of nitrogen substitution is due to the combination of inductive and the resonance effect, as can be seen by comparing the base ionization constant of 3-nitroaniline, 3-nitroaniline and 3-nitroaniline, a combination of inductive and resonance effect, as can be seen by comparing the base ionization constant of 3-nitroaniline and 4-nitroaniline. So here you can see the due to the inductive and the resonance effect. So the due to the inductive and the resonance effect, there is a decrease in the basicity. There is a decrease in the basicity. There is decrease in the basicity on the nitro substitution. There is a decrease in the basicity on the nitrogen substitution, which is due to the combination, inductive and resonance, which is due to the combination of inductive and resonance effect. And this can be seen by comparing. If we are comparing the base ionization constant of 3-nitroaniline. So here we are. So the pKb of this 3-nitroaniline is your 11.53, and the pKb of this nitroaniline is 13.0. So here there is an decrease in basicity on nitro substitution, which is due to the combination of inductive and resonance effect, and this can be seen by comparing the base ionization constant of this 3-nitroaniline and the 4-nitroaniline. So note that the conjugate acid of 4-nitroaniline is a stronger acid than phosphoric acid. So here the nitroaniline, the conjugate acid of 4-nitroaniline is having is a stronger acid. This is a stronger acid. This 4-nitroaniline is a stronger acid than phosphoric acid. So here this heterocyclic aromatic amines are weaker bases than aliphatic amines. So that is why the heterocyclic aromatic amines, they are weaker bases. Than the aliphatic amines, and then when a nitrogen atom is incorporated, directly into an aromatic ring, its basicity depends upon the bonding contrast. For example, in pyridine ring, the nitrogen lone pair occupies an sp2 orbiter, which is not a part of the aromatic sextet. So here, in the substitution effect, the secondary The second factor that is contributing in this decreased basicity of the aromatic ring, aromatic amines, this is due to the electron withdrawing effect of the sp2 hybridized carbons that are present in the aromatic ring, aromatic amines, and uh, which are compared with the sp3 hybridized of the aliphatic sp3 hybridized carbon of the aliphatic amine. So the unshared pair of electrons on nitrogen. So the unshared pair of electrons on nitrogen in an aromatic amine is pulled towards the ring and therefore less available for protonation to form a conjugate acid of the amines. So the electron releasing groups, for example, are the ethyl, and ethyl, and other alkyl groups. These are increasing the basicity of the aromatic amines, whereas the electron withdrawing groups, these are decreasing the basicity of the aromatic amines. So the decrease in the basicity on halogen substitution is due to the electron withdrawing inductive effect of the electronegative halogen, and the decrease in basicity on nitrogen substitution is due to the combination of inductive and resonance effect, as can be seen by comparing the base ionization constant of 3-nitroaniline, which is pKb equals to 11.53, and 4-nitro-pKb equals to 13.0. So here the conjugate acid of this 4-nitroaniline is a stronger acid than phosphoric acid, and the heterocyclic aromatic amines are weaker bases than aliphatic amines. And when a nitrogen atom is incorporated directly into an aromatic ring, its basicity depend on the bonding context. And for example, in the pyridine ring, that is a heterocyclic aromatic amine, it's the lone pair occupies an sp2 orbital, which is not a part of the aromatic sex tag. So here, so in case of heterocyclic aromatic amines that are bases than aliphatic amines, in this the nitrogen atom is incorporated directly into the aromatic ring. The nitrogen is present in the ring itself. So its basicity depending on the bonding. So in this, this is in this also reality basis, because the nitrogen lone pair occupies sp2 hybridization, and which is not a part of aromatic sex type. So here, next, so this electron pair is not part of the aromatic sextet. So here, when it is reacted with this water molecule, so there is a compound that is formed, and the aromacity is maintained even when protonated. So so the aromacity is maintained even when protonated, means if there is the addition of this hydrogen on this nitrogen, that is, and then also there is the aromacity of this ring is also maintained. So here the proton transfer from water or other acid to pyridine does not involve the electrons of the aromatic sextet, and the pyridine is a weaker base, and the pyridine is a weaker base than aliphatic amines, because the unshared pair of electrons of the pyridine nitrogen lies in sp2 hybrid orbital, whereas in aliphatic amines the unshared pair lies in sp3 orbital. So the electrons in sp2 hybrid orbitals are held more tightly by the nucleus than the electron in sp2 hybridized orbital. So the when this proton is transferred from the water to this pyridine, then it does not involve the electron of the aromatic sextet. So this pyridine is a weaker base than aliphatic amine, because the unshared pair of electrons of the pyridine is nitrogen. So the unshared pair of electrons of the pyridine nitrogen lies in sp2 hybrid orbital, whereas in aliphatic amine, the unshared pair lies in sp2 hybrid orbital, and electrons in sp2 hybrid orbital, that is forming a 33% of your S character, they are held more tightly by the nucleus than the electron in sp3 hybrid orbital, that is having the 25% S character. And in this effect that decreases, is the basicity of the electron pair on sp2 hybrid nitrogen compared with that on sp3 hybrid nitrogen. So here you can see that this nitrogen pair is not a part of this aromatic sextet, and this electron pair is a part of this aromatic sextet. When it is dissolving with the water molecule, then this there is a aromaticity is maintained, and even when protonated, and therefore there are two nitrogen atoms in imidazole. This is the structure of the imidazole, and in this imidazole there are two nitrogen atoms that are present in this imidazole, and each is having a two pair of unshared electron pair, and one shared pair lies in the 2p orbital. One shared pair means that is shared, that is lying with the 2p orbital and in an integral part of the 4n plus 2 pi electrons of the aromatic system. The other unshared pair lies in the sp2 hybrid orbital and is not part of aromatic sextet, and it is not a part of your aromatic sextet, and it is a pair of electrons not part of the pi system that functions as a proton acceptor. So here the other unshared pair of electron, one part of this bunch unshared pair is shared, and it is live in the 2p orbital, and it is an integral part, of an 4n plus 2 pi electrons of the aromatic system. And the other unshared pair, the other unshared pair lies in an sp2 hybrid orbital, and this is not a part of the aromatic sextet, and it is a pair of electrons. It is a pair of electrons that do not. It is a pair of electrons and that not part in the pi system that functions as proton acceptor. So in this, it is having the 33% of S character, and it is having the 25 S character, and in this effect is decreasing the basicity of this in this. Yes, in this the electron in sp3 hybrid orbital that is having the 33% and S character are held more tightly. So this sp3 hybrid orbital, it is held tightly by the nucleus, and the electron in sp3 orbital compared to this sp3 hybrid orbital, and it is this effect that decreases, and due to this there is a decrease in the basicity of the electron pair on sp2 hybrid nitrogen compared with that of the sp3 hybridized nitrogen. And in this case, this is a structure of the imidazole. In this imidazole, there is a presence of two nitrogen atoms that are present on this imidazole, and both are having the lone pair. Each one of the nitrogen is having the unshared pair of electrons. So here you can see that the one nitrogen's electron pair are participating as a part of your aromatic sextet, but in case of the another nitrogen that is not a part of this aromatic sextet, and when it is dissolving with the water molecule, so there is a formation of a product, and this product in the imidazole, this atomicity is maintained. This atomicity is maintained even when protonated. Means here, if in this case their atomicity is maintained if the proton is added to the nitrogen atom, and there are two nitrogen atoms. There are two nitrogen atoms in imidazole, each with an unshared pair of electrons, and one shared pair lies in 2p orbital and in an integral part of 4n plus 2 pi electrons of the aromatic system, and the other unshared pair lies in an sp2 hybrid orbital and is not a part of the aromatic sextet, and it is a pair of electrons not part of the pi system that function as a proton acceptor. So this nitrogen electron pair is a part of the nitrogen, but this nitrogen, its electron pair, these are not the part of the pi system. These are not the part of the pi system, and but they are accepting a proton. And the other unshared pair lies in an sp2 hybrid orbital and is not a part of this not a part of this aromatic sextet. So this is not a so this in this the heterocyclic aromatic compound, the aromacity is obtained even when protonated, and the two other nitrogen is not participating in this heterocyclic ring, and the one nitrogen which is protonated already, that is taking a part of this aromatic sextet. So next is in pyridine, the unshipped pair of electron functioning as the proton acceptor, and in imidazole, lies in sp2 hybrid orbital, and imidazole lies in sp2 hybrid orbital and has decreased basicity compared with an unshipped pair of electron in sp3 hybrid orbital, and the positive charge on the imidazolium ion is delocalized on both nitrogen atoms of the ring, and therefore imidazole is a stronger base than pyridine. So this imidazole is a strong basis than the pyridine, because in this imidazole there are two nitrogen, but is participating in the sextet, aromatic sextet, but the second is not participating in the aromatic sextet. But in case of pyridine, only one nitrogen is present in this pyridine, and that is not participating in the aromatic sextet. So next is the preparation of alkyl and phenylamine. So the alkylation of ammonia, Gabriel Elimide synthesis, Hoffman bromamide synthesis, reduction of nitrile, reduction of oxens and acid amides, reduction of nitroarenes, reductive amination of aldehyde and ketones are methods commonly So here, these are the commonly used for preparing amines: the alkylation of ammonia, Gabriel Thalamide synthesis, Hoffman's bromide synthesis, reduction of nitrile, reduction of oxens and acid amides, reduction of nitroarenes, and reductive amination of aldehyde and ketones are methods that are commonly used for preparing amines. So these are the methods that are used for preparing the amine. So the first is your method for the preparation of all three type of amines along with cautionary ammonium salt. So there the first method we are using here for the preparation of all three type of amines along with cautionary ammonium salt. Second, so for alkyl halides, this is the Hoffman method, and in the Hoffman method, when alkyl halides are heated with an aqueous or alcoholic solution of ammonia in a closed reaction vessel at about 100 degrees centigrade, then a mixture of primary, secondary, and tertiary amines along with the quaternary ammonium salt is obtained, and the primary amine is obtained by the replacement of halogen as halide by ammonia, and now this primary amine acts as a nucleophile and attaches itself to the alkyl halide molecule to produce the secondary amine. Again, this secondary amine acts as a nucleophile and attach itself to the alkyl halide molecule to give the tertiary amine. So at last, the tertiary amine attaches itself to the alkyl halide molecule to form the quaternary ammonium salt, and the process is as follows. So in the Hoffman method, from the alkyl halides, there is the formation of this quaternary ammonium salt, and in this, when alkyl halides are heated, firstly, when they are heated with an aqueous or alcoholic solution, they are heated with the aqueous or alcoholic solution of ammonia in a closed reaction vessel at about 100 degrees centigrade. Then a mixture of, there is a formation of a mixture of primary, secondary, and tertiary amine, and there is a formed, and which is formed with a quaternary ammonium salt is obtained. So from this alkyl halide, there is formation of this primary, secondary, tertiary amines, and then there is a formation of this quaternary ammonium salt is formed, and the primary amine is obtained by the replacement of halogen as alkyl halide by ammonia, and now this primary alkane, and from this primary amine again there is the addition of this alkyl halide, and this primary amine is acting as a nucleophile, and the alkyl halide molecule is attaching or forming a bond with this alkyl primary amine, and then there is a formation of the secondary amine. Next, the secondary amine is reacted with again the alkyl halide, and this secondary amine is acting as a nucleophile, and this attaches to this alkyl halide, and there is the formation of this primary, this tertiary amine. Again, from the tertiary amine, the nitrogen, this alkyl halide is reacting with this tertiary amine, and there is a formation of this partially ammonium salt. So the process is as follows. So in the process, in the reaction, we can see here that this is the alkyl halide, and when it is reacting with this ammonia, there is a formation of this primary amine. Again, this primary amine is reacted with this alkyl amine, and there is a formation of the secondary amine. The secondary amine again is reacted with this alkyl halide, and there is a formation of this tertiary amine. So in this reaction, we can see that here there is the addition of this alkyl group to this primary amine, and there is a formation of the secondary amine, and there the removal of one hydrogen is happening. Again, from this secondary amine, there is a removal of this nitrogen, and there is a formation of this tertiary amine. And from this tertiary amine, again there is a addition of this alkyl group, and there is a formation of this quaternary ammonium salt is formed here. So here we have taken the example of this methyl bromide. When it is reacted with this ammonia, there is a formation of this methylamine. Again, when this methylamine is reacted with this methyl bromide, there is a formation of this dimethylamine, and from this dialkyl amine, again there is an addition of this alkyl halide, and there is a formation of this tertiary amine, and after that there is a formation of this quaternary ammonium salt. Next is by the action of ammonium alcohol. So that is this method is also known as Sabatier and Meillet method. And in this, when alcohol vapors with the ammonia are passed over a bed of alumina, and this on silica gel at about 360 degrees centigrade, then there is the formation of a mixture of amines along with the partial ammonium salts are obtained. So in this, C2H5OH plus ammonia, that is reacting with this alumina at 6 degrees centigrade, there is a removal of water molecule from here, and there is a formation of this ethylamine. After that, again this alcohol is attached, ethanol is attached to this, and there is a formation of diethylamine, and from there the water molecule is moved out. From the diethylamine, again it is reacted with this ethanol, and there is a formation of this triethylamine, which is a tertiary amine. So this method yields a mixture of primary, secondary, tertiary amine along with quaternary salts, which are separated from each other by means of Ginsberg method or Hoffman method. So, however, primary amines can be prepared in good yield by using excess of ammonia. Next is from carbonyl compounds. So, on heating with an acidic solution of nather, ammonia, or amine, carbonyl compounds are converted into amines. So, this in this case, this carbonyl compound aldehyde, this acetaldehyde, this is reacting with this ammonia, and there is a formation of this amine, and after that there is a reaction in the presence of this catalyst, that is a nickel, and hydrogenation is happening, and there is a formation of this amine. So this reaction is called as reductive amination of aldehyde. So using this reductive amination of primary amine, secondary amine can be formed. So here this is your propaldehyde. So in this, propaldehyde is formed, reacted with this primary amine, and there is a formation of this amine, and after that it is again reduction is happening in the presence of nickel, and there is a formation of this secondary amine. Next, by the reduction of amide. So in the reduction of amide yield primary amines on reduction by lithium aluminium hydrides, while N-substituted and N-disubstituted amine produces secondary and tertiary amines respectively. So this acetamide, when it is reacting with this lithium aluminium hydride and hydronium ion, there is a formation of this ethanamine, which is the primary amine, and this N-methyl acetamide is reacting again with this catalyst, that is the lithium aluminium hydride. So there is a production of this secondary amine. So here from the amides there is a production of the ethanamine, but from the N-methyl acetamide there is a production of the N-methyl ethanamine, which is the secondary amine. So again, from the N-dimethylacetamide, there is a production, there is a preparation of this tertiary amine. So this tertiary amine is formed from the this N-dimethylacetamide. So there is a reduction of amide. Means there is an addition of hydrogen in the presence of your lithium aluminium hydride. Next, by the additional method for the preparation of primary amine. So by this, the first method is by the reduction of nitroarenes. So in this, the aromatic amines are normally prepared by the reduction of corresponding nitroarenes in the presence of hydrogen and draining nickel and the tin and L-hydrochloric acid, iron and hydrochloric acid with zinc and acetic acid or ammonium hydrogen sulfide. So in this, by the reduction of nitroarenes, the aromatic amines are normally prepared. These aromatic amines are normally prepared by the reduction of corresponding nitroarenes. Means from the nitroarenes, these are forming a primary amines, and the nitroamines are reacting in the presence of the hydrogen, draining nickel, and the tin and the hydrochloric acid, iron and the hydrochloric acid, zinc and the acetic acid or ammonium hydrogen sulfide. So in the catalytic reduction, the these nitro compounds are reduced. To amines with the hydrogen gas in presence of powdered nickel. So this nitrobenzene is reacting in the presence of, there is a reduction is happening here. So here reduction is happening in the presence of catalyst, that is the nickel. So the reduction with the hydrogen, this nitrobenzene, there is the addition of this hydrogen in the presence of the nickel catalyst, and this is the formation of this aniline plus water molecule. So this is the first method for the preparation of primary amine, and this is the by the reduction of nitroarenes. So from the nitroarenes, there is a formation of this aniline, that is the primary amine, and that are formed from the nitro compound and by the catalytic reduction in the presence of your nickel catalyst. Next is the reduction with the stannous HCl or FeCl, HCl or zinc CH3C acetic acid. So the nitro compounds are also reduced with metal and concentrated hydrochloric acid like HCl, FeHCl or zinc acetic acid into amine. So this nitrobenzene is reacting with hydrogen in the presence of stannous HCl, and there is a formation of this aniline plus water molecule. Third is your partial reduction with NH4SH. So by the partial reduction, one of two nitro group in a dinitro compound is reduced into amino group by using ammonium hydrogen sulfide as reducing agent. So in this, the partial hydrogenation, in the partial reduction of from this ammonium hydrogen sulfide. So here one of the two nitro groups in a 9-nitro compound. So this is a 9-nitro compound, and this is reduced in the presence of this ammonium dihydrogen sulfate, and this is converted into your amine compound. So one nitro in the dinitrobenzene is converted to the amine in the presence, because there is a reduction. Reduction is happening in this reaction. Next, by the reduction of nitrile or cyanide. So the carbon hydrogen triple bond in a nitrile or cyanide can be reduced by the reaction of hydrogen gas in presence of a metal catalyst like nickel, palladium or lithium aluminium hydroxide. So here, for example, methyl nitrile is reduced by hydrogen and nickel to ethyl amine. So this methyl nitrile is reacting with this, in this methyl nitrile, there is a reduction is happening in this methyl nitrile, and there is a formation in the presence of nickel, and there is a formation of this ethylamine. There is a formation of this ethylamine. So the phenyl methyl cyanide is reduced by hydrogen and nickel or by lithium aluminum hydroxide to phenyl ethylamine. So this, in this reduction of nitrile or cyanide, this nitrile or the cyanide is reduced in this. If there is a reduction is happening in this nitrile and the cyanide, and there is a formation of this phenyl ethylamine. Next is your by the action of ammonia on phenol. So the ammonia is reacting with the phenol in the presence of this chloride at 300 degrees centigrade. There is a formation of this aniline. By skimmed reaction, in this, the aromatic amines can be obtained by the treatment of aromatic carboxylic acid in concentrated sulfuric acid with chloroform solution of hydrozonic acid. So these are from the benzoic acid, the aniline is formed. By the reduction of oxime, so oxime is primary amine by the reduction by sodium or ethanol or by lithium aluminum hydroxide. So by the action of chloramines with Grignard reagent. So in this, the primary can be obtained by the action of chloramines on Grignard reagent. So this is a chloramine and this active with a Grignard reagent, and there is a formation of the methylamine and the tertiary. Next, by the decarboxylation of amino acids. So when an amino acid is heated with barium hydroxide, it loses CO2 and forms a primary amine. So this glycine forms ethyl amine. So the Hoffman bromamide reaction, in this the amide are reacted with this bromine and then potassium hydroxide is the formation of amine potassium carbonate KBr plus H2O is formed. So this is the acetamide which is reacting with bromine and there is a formation of methylamine. Similarly, benjamide is reacting with bromine and KOH brings the formation of this phenylamine. So this is the mechanism of this. In this step first, this potassium hydroxide is reacting with bromine and there is a formation of KBr. After that, this acetamide is reacting with this OBr negative that is forming an intermediate. Next, this bromamide is forming a bromamide anion. This anion is reacting and there is a formation of this acyl nitrine. So this acyl nitrine is forming an isocyanide and from this isocyanide there is a formation of this amine. Now the question, the nitrogen atom of the amino gives a hybridized sp hybrid. How many structural isomers are possible? 4. Next, this is not represented by the amines, that is your functional ammonium salt, and the correct aliphatic name is your A. Next is your amines which are bonded in alkyl groups are as primary, and the trimethylamine is an example of tertiary amine. So these are the references of this topic, and thank you so much for today's lecture.